Well, there's a lot of interesting discussion these days in the field of the neuroscience of pain, especially as it relates to various psychological phenomena that have been well studied in other contexts, such as the placebo effect or expectancy effects. It very well may be that these effects are mediated via projections that modulate how this periaqueductal gray then mobilizes the resources of the brainstem to modulate the transmission of nociceptive signals in the dorsal horn of the spinal cord. So stay tuned. I'm sure we will learn much more about these mechanisms in the years to come. And now let's turn our attention to feed-forward modulation of nociception. And this gets us into a really fascinating discussion of an idea that's more than 50 years old now, and it's called the gate theory of pain. And the idea essentially is this, that somewhere in the central nervous system there is competition between the signals that are being driven from our mechanoreceptor afferents and those that are driven from our nociceptive afferents. And this competition potentially can allow for a mechanoreceptor to close the gate on the transmission of pain signals. Well, here's one circuit that was proposed by Melzack and Wall about 60 years ago that attempts to provide a way of understanding why we do something as simple as squeeze a finger after we've hit it with a hammer. Well, the idea is that in addition to the usual projection to the dorsal columns that our mechanoreceptor afferent might provide, perhaps there's a collateral that synapses on one of these small interneurons in the substantia gelatinosa that potentially can inhibit the transmission of pain information from, let's say, an A delta afferent synapsing upon a dorsal horn projection neuron. Well, if we imagine that this A beta fiber conveying mechanosensation fires action potentials that converge upon such an interneuron, then perhaps the effect is to suppress the firing of our C fiber afferent on the dorsal horn neuron. And this conceptually would be a paradigm for closing the gate on pain transmission. So getting back to hitting your thumb with a hammer, our first impulse often is to squeeze that thumb that's just been struck. Well, I think what our impulse is driving us to do is activate mechanoreceptors. And that competition between nociceptors and mechanoreceptors might be playing out in the circuitry of the dorsal horn of the cervical spinal cord as we squeeze our thumb, such that what we actually experience then has more to do with the sensations that are driven by the mechanoreceptors than those that are driven by the nociceptors. Well, this is a rather vague concept that I think still remains to be well established in the neuroanatomy and the neurophysiology of the circuits of the dorsal horn. But the idea itself has been very powerful, and it's led to a number of new interventions that are aimed at closing the gate to pain transmission, perhaps at other levels. For example, one surgical intervention now to address some forms of pain would be to stimulate with a microelectrode the dorsal columns of the spinal cord. So the idea would be that perhaps there is another gate, or maybe a series of gates at higher levels of processing along our somatic sensory pathways, perhaps in the thalamus, or perhaps in the cortex itself. And by activating mechanosensory fibers, perhaps the gate to the transmission of painful information can be shut. Well, let's move on now and talk about a few remaining topics before we wrap up. And let's just spend a few minutes thinking together about chronic pain. Well, chronic pain is a huge problem in societies around the world. It's the source of untold disability and suffering from people from all walks of life. And chronic pain can usually be conceptualized as either being related to some nociceptive source or not at all. So there is a nociceptive chronic pain that results from ongoing stimulation of nociceptors. You might imagine that there's some ongoing site of inflammation or injury to peripheral structures that continues to drive afferent activity in our nociceptors. Such forms of chronic pain would stimulate both our A delta and our C fibers, and so one would expect both first and second pain sorts of signals. There's also a chronic pain syndrome that has largely remained somewhat of a mystery to medical neuroscience. Typically, this is a syndrome of chronic pain when there is no known nociceptive etiology. Examples might include some individuals who suffer with chronic low back pain, perhaps fibromyalgia. That doesn't mean that there is not a nociceptive source. It's just that to date, none has been discovered when we apply this label of chronic pain syndrome. The actual etiology, therefore, remains poorly understood, but in most cases, we consider it to be not a matter of a psychogenic etiology, but rather just an etiology that remains poorly understood in terms of the fundamental neuroscience that underlies the source of these signals that are interpreted as pain. There have been a variety of recent proposals about where these chronic pain states might come from. One idea that is under investigation is that perhaps there's some dysregulation of those feedback descending systems that run through structures like the periaqueductal gray and ultimately through the brainstem and into the dorsal horn of the spinal cord. Some dysregulation of the brain's intrinsic means of dampening down nociception potentially could lead to sustaining a chronic pain state. But undoubtedly there's more to it than that, and probably a lot more interesting neuroscience involved. Which leads us to our final topic, and that would be neuropathic pain. So neuropathic pain refers to pain that arises because there's abnormal activity in a nociceptive pathway that's unrelated to the presence of a nociceptive stimulus out in the peripheral structures of the body. Well, one can imagine at least two kinds of sources of this kind of abnormal activity. One could be if there's direct compression on a nerve, and that compression can cause there to be a physical opening of ion channels in the membranes in that region of the compression. Should that be the case, one can imagine the development of an ectopic focus for the generation of action potentials that then propagates centrally, and ultimately the central nervous system interprets that as pain. So nerve compression can be a common peripheral cause of neuropathic pain. Now, if that's the case, one might expect there to be other accompanying sensations, and often that is the case. There are paresthesias, which is a term that's used to describe just unusual somatic sensory sensations that don't commonly map on to the usual experience of encountering a mechanical stimulus. Well, this is one common scenario where neuropathic pain can be trouble, but neuropathic pain can also arise through central mechanisms. So among the central causes of neuropathic pain would be the sustained sensitization of neurons in a nociceptive pathway. We've already talked some about this phenomenon of wind-up. One can imagine if neurons in the dorsal horn of the spinal cord, for example, stayed in that state for an extended period of time, then that might lead to the development of a chronic pain condition. Another idea about neuropathic pain is that perhaps it's a reflection of abnormal autonomic nervous system output to visceral structures, including perhaps even the vasculature. So one idea is that maybe the sympathetic outflow to the viscera is dysregulated in some way, and then visceral sensory inputs back into the nervous system are what's driving this interpretation of pain. But I think perhaps the most interesting idea that's emerged in recent years is the notion that neuropathic pain may arise because of plasticity that's become maladaptive for human behavior. And this maladaptive plasticity might be sustaining the chronic pain state. One prime example of such phenomena might be those that are affiliated with phantom limbs. So phantom limb sensations are those that are generated following a nerve injury or limb loss, either through trauma or through surgical intervention. And here before us are illustrations of what some patients have reported to be the sensations associated with body parts that are no longer present. And you can see that these sensations take a variety of forms. Sometimes there's nearly a complete sensation of the missing limb. Sometimes it's only a partial sensation of that missing limb. Sometimes there's this phenomenon of telescoping, such as what we find here, where the more distal part of the missing limb feels like it's more proximal than it actually would be were the limb intact. Well, these sensations, I think, really capture what I started off telling you about, and that is that pain is a tremendously complex phenomenon. It involves more than just nociception, but perhaps even more significantly, it involves how those nociceptive signals become integrated into our conscious awareness. And that phenomenon is one that I think will continue to be a problem in healthcare, but also I think neuroscience offers wonderful opportunity to approach this problem through new multidisciplinary means. One might imagine, for example, if the problem of pain really is one of maladaptive plasticity in the forebrain, then there may be different ways to intervene that don't necessarily work through the peripheral channel that might have triggered the pain in the first place. Perhaps this is why social structures, why physical exercise often can be such a benefit to people that are experiencing pain states. Well, there's much more research that needs to be done in this fascinating field of pain and pain management. And I hope that you all might have an opportunity to contribute to the advancement of this field and the alleviation of human suffering. But in the meantime, let's apply ourselves well to the studies of the mechanisms of nociception and to the organization of the central pathways that convey nociceptive signals into the nervous system and on up to the levels of the cerebral cortex. So if you've not yet looked at the tutorial on the pain pathways, you might want to go ahead and cue that up next. So I'll see you there when we briefly review the pathways for pain transmission in the central nervous system.